Hello everybody, welcome back. Good to be with you again today. Today we are going to be hitting a new section in the textbook. We're going to hit 10.5. It's on tangents. So hold on to the seat of your pants because it's going to be a wild ride. Alright, so first thing first, let's talk about what a tangent actually is. In the case of geometry in this world we're living in this year, we're talking about a tangent as a line that's in the same plane as a circle, and it intersects the circle in exactly one point. So when you move on and later on you get to what a tangent is in a calculus class, when you get there, you're going to talk about a line being tangent to the curve. You can no longer talk about it just intersecting the thing at one point. It's going to be something whose where the slope is shared by the function. It's going to be something a line whose slope matches the function at the point where it intersects. But for now, in circles, we can deal with this being the definition of a tangent. Okay, it's a line that intersects the circle at exactly one point. Okay. All right. So next, the point of tangency. That is the point where this tangent intersects the circle. It's called a point of tangency. And next, we have that our common tangent is a line, segment, or ray that is tangent to two circles in the same plane. So that can happen a lot of different ways. Okay, so I'm just going to draw a little bit on here while y'all are copying the rest of these these definitions down. If I have these two circles in a little, let me fix that. Okay, so just pretend I did a better job of drawing a circle right there. And if I have there where they kind of just barely touch at one spot, then that line that's tangent there at that point where they intersect is going to be a common tangent. That's one way. Another way to get a common tangent on circles is, for example, something like this, where it is tangent to the big circle at this point and the little circle over here at this point. So that is also a common tangent to these two circles. So you have lots of different ways where you can end up with common tangents. Okay, it's a line, segment, or ray that is tangent to two circles in the same plane. Okay, let's talk about some more of our things. We're going to talk about a couple theorems now. In a plane, a line is tangent to a circle if and only if it is perpendicular to a radius drawn at that point of tangency. So I'm actually going to draw a little circle here. All right, and here is me a little tangent line here. This thing is only going to be a tangent line if the line I'm drawing from the center, which you can see about right there, when I go to this circle, or to this tangent line, when I go to that point, that makes a right angle. Okay, that's the only way that we are going to end up saying that we have a tangent line. Okay, is if that line makes a right angle with this line that we are thinking might be a tangent. Also, if I end up with a perpendicular by taking a radius out to some line, then I can tell you that that line is in fact a tangent line. Okay. All right. So next, if we have two segments from the same exterior point and they are both tangent to a circle, then those line segments are going to be congruent. Okay, so if I have some other segment coming from out here, whoops, and we say, hey, what's going on with this one, and we let it be tangent. Okay, let's say that they're both starting at the same point. Then what I can tell you is from that point of tangency here, and that point of tangency here, out to this point where they intersect, these two lines would be congruent. Okay? That's a really big one for this one. We're going to use that one a lot in here, and it's going to kind of carry on into another section as well. All right. Last little thing that you need to make sure, the last piece of big information that you need to get from this is that a polygon is circumscribed about a circle if every side of that polygon is tangent to the circle. So over here on the left, you have some circumscribed polygons, which you can see that each one of the sides of that triangle is a tangent to the circle. Same with that quadrilateral, and same thing with that hexagon. And then over here on the right, these are some examples of polygons that are not circumscribed. Okay, so whereas on looks like that middle one over here with this rectangle, right here, we do have three sides tangent, but that fourth side of that rectangle is not tangent to the circle. Okay, the one right here, that circle is completely contained inside the hexagon, but there are no tangent lines to it. And over here, the circle is not completely enclosed inside the triangle, so again, it cannot be circumscribed about the circle. Okay, so that's the big information you need from this. That's all the information you need. That's all the new stuff you need to hold on to. Let's see if we can go through some examples and see if we can kind of figure out how to apply some of this now in the course. Okay, so our first example, I'm just going to draw some common tangents and see if we can find any places where we've got tangent lines that are common. Okay, so for this one right here, that is a tangent line that is, to me, that looks like it is common to both of those two circles. But I seem to be having a harder time getting one going the other way. Maybe that would be one right there as well. Okay, for A. For B, okay, again, I'm going to take this long path in. It's all about finding that right path. And this one right here, those both appear to be common tangents. On C, let's see if we got any common tangents here. Alright, let's see that one in kind of a green color. We got this place where they barely touch, right there. And then I'm going to have one coming across here, and one coming across there. On this one here in D, it looks like maybe just at that intersection point there. So each one of them has a common tangent, whether or not the one, as long as they intersected somewhere, if one of them's inside the other one. So if they intersect, just barely touch, like it intersect at one point, then we know we've got a tangent. If they are overlapping or separated, we can probably draw a common tangent to connect them. Okay, so that's good. Let's get into this next example. If JL is a radius of circle J, I want to know if KL, this line KL, is tangent to J. Okay, so if I know that this right here is 8, then I know that right there is 8. So that means I have a right triangle with 3 sides. This side KJ is going to be 9 plus 8, or 17. So I have 3 sides of this right triangle, 8, 15, and 17. We can check to see this is the right triangle by checking to see if Pythagorean theorem holds. So we're going to say 8 squared plus 15 squared is going to equal 17 squared. Alright, so 8 squared is 64. 15 squared is 225. And then we need to get 17 squared, which I don't actually have memorized. So let's see, 17 times 17, 289. And let's see if those match. Yep, 64 plus 225 is in fact 289. So yes, this is in fact a right triangle. Okay, that is my justification. Pythagorean theorem holds, must be a right triangle. Next, I'm told that this line JH is a tangent, okay? So I'm given that piece of information. I know that that's true, so I know that that right there must be a right angle. So I would like to find the value of x. What this tells me is that x plus 8, that's that big side, squared, must equal x squared plus 12 squared. X plus 8 squared is x squared plus 16x plus 64. That needs to equal x squared plus 144. If I subtract x squared from both sides, those terms would go away. If I subtract 64 from both sides, I'll end up with 16x is equal to 80, or x is equal to 5. Alright, so hopefully that feels good. You know, I noticed that I had a right triangle, so I used Pythagorean theorem, pretty similar to the way I worked with the second example. Alright, so again, I'm trying to use the information that is given to me in these problems to be able to create something that I feel like I can solve. Okay? Alright, so let's look at example 4. In this one, they tell us that we have two tangent lines, things that are two things that are tangent to this circle D, and they're both originating from the same exterior point. That means, according to one of our theorems, that these two lines must be equal to each other. So that must mean that x plus 15 must equal 2x minus 5. And lo and behold, they actually want me to figure out what x is. So I'll subtract x from both sides and get x, and I'll add 5 from both sides and get 20. So x would be equal to 20. Okay, again, this is just very simple. Use the information given to me to solve something inside this circle. Alright, and our last main example before we get to a couple guided practice problems, I want you to look at this one for a moment. Okay, we have this triangle set up here around the outside of a circle, and I've got that circle, or that triangle is circumscribed about that circle. I'd like to find the perimeter. So this is what I know. I know then, if it's circumscribed, that this line here, and this line here, and this line here are all tangents. That means to me that A to D, right here, is congruent to A to E, meaning that side is also 8. It also tells me that B to E, right, has got to be congruent to B to F. So that side right there from here to here would be 7, which means that what's left from F to C would be 3. And that's going to be important to me because also these next two things are tangent, right, coming in from the same exterior point. So that means that these lines are also congruent, so this last part over here is also 3. They'd like me to find the perimeter. The perimeter is going to be what happens when I add up the things going around. I've got a side of 10 over here, so I've got basically 7 plus 3 plus 3 plus 8 plus 8 plus 7. Or I have 7 and 7 is 14, 3 and 3 is 6, 8 and 8 is 16, or I have 36. That is the perimeter of that triangle. Alright, so this was a nice little application problem they put at the end. This is supposed to be, that's kind of supposed to be like the, ooh, we got a little harder there. But hopefully that feels fairly straightforward with that process, okay? Recognizing where I've got tangents coming from the same exterior point, marking those things as being equal to each other, and then kind of deducing down those distances. Alright, so let's get to some guided practice and let's look at these. We've got just a couple more examples to get through, and then we have finished this section, okay? If you look at both A and B in this first guided practice problem, alright, you're going to notice that they are very similar, very similar to the problem we worked over here in example 3. We've got a line that is tangent to a circle right here. We're going to assume that BC is tangent to circle A. I would like to figure out what X is. Same thing is true in the B example. I've got QS is, we're getting to assume that that is tangent to the circle R, and I'd like to find out what that little X is. So I want you to kind of think real quick about how you would solve this C section. So I want, if anybody's up there near the video, please, if you can go ahead and pause it real quick so that we can get you to think about how to work these two problems. I'd like you to work these two problems, and once we've taken a couple minutes to try to solve these or get them set up on our own, then I'd like somebody to come back, hit unpause, and we'll see how you did. Okay, so you should be pausing it now. Okay, I take it by now that you've paused it. Okay, so if you haven't paused it, do it now. I'm starting to go through the solution. All right, so we should be going through the solution now. In this first one, this is a right triangle. If I want to find x, I'm going to use the property of Pythagorean theorem that x squared plus 14 squared needs to equal 17 squared. Okay, x squared plus, then that would make 196 needs to be equal to, if I remember correctly, 17 squared that we did earlier, yep, was 289. So 289. Alright, so that means that x squared is going to be equal, what happens when I subtract 196 from 289, and that would be, I think, 93, let's see, 96, let's see, yep, I get 196 here. Let's see, we'll subtract it like that. We'll just do it the long way. 3, that would be a 18, excuse me. And yep, that would be 93. Okay. Good for me in my math today. And so we're going to come up here, and that means that x is going to be equal to, could be plus or minus, but in our case, since x appears to be a measurement, we're going to say it's the square root of 93. Okay. Alright, so that's pretty good for that one. Hopefully that was where you headed for this one. It's okay that our answer is a square root. We're just going to leave it like that unless they tell me to round, okay? So I'm going to leave it like that as the good mathematical answer. Alright, next, we've got this problem. This one's a little bit more similar to the other examples. Hopefully you've also had a chance to work this one. If you haven't, pause it, work it, see how we do. This is close to another example that we worked. Alright, so I'm going to start going through the solution here. Hopefully you've had a chance to try it. This is x. What we have now is that x squared plus 4 squared is equal to x plus 2 squared. Right, this is just like example 4, I believe. Okay, or in our case, what this means is x squared plus 16 is equal to x squared plus 4x plus 4 when we square all that out. Alright? Make sure you are distributing that stuff when you do that x plus 2 squared. Okay? Don't lose track of that middle term. Alright, so when I go through and subtract x squared from both sides, I'm going to get this. I'll subtract 4 from both sides and get 12 is equal to 4x, or x is equal to 3. Okay, that feels good, right? Hopefully you did really well on that one. Alright, let's go down to the second guided practice and take a look at it. Let's set it up, and then I want y'all to pause it again after I've set it up so that you can try to solve these on your own, okay? So again, here we have a couple of tangents to circles on both situations in both A and B. We've got these two tangent lines that are originating from the same exterior point, and I want to use that information to try to solve for x. Okay, it doesn't say, oh yeah, there it is, find the value of x. So that's what we want to do. If you see this here, okay, you'll go ahead and pause it now so that you can try it on your own, then come back and see if we got the right answer. Alright, I'm taking it that you paused it, and now you are back. So we are going to work through this problem. This first one, that means if these things are tangents from the same exterior point, I can set these things equal to each other. That means 26 is equal to 3x plus 8. Subtract 8 from both sides, and get 18 is equal to 3x, or x is equal to 6. Okay, good. Let's try the other one. Same thing's going to be true. Those things got to be equal to each other. So 2x plus 9 better equal 3x plus 6. Or in that case, subtract 2x from both sides and you'll get x. Subtract 6 from both sides and you'll get 3. And x is equal to 3. If you feel like you've got those, if you feel like you understand what's going on, then you're going to be just fine, okay, in this section on tangents, okay? Again, it was fun. We'll try to get through 10.6 on Monday. And then I'll try to give you all some time to practice some stuff for a day, maybe on Tuesday. Then we'll get through 10.7 and 10.8 and have a couple days of a little bit of a review before you take a test, okay? Make sure y'all are studying up on this stuff. I really expect you guys to be going through this information and spending some time looking at these theorems and practicing some of these problems on your own. Okay, it's very important that you spend time looking at these theorems because right now, if you've paid attention, you know, over here, we've already gone through a whole lot of things. You know, our theorems went all the way up to 1011. So we're already at 11 theorems and we've had a whole lot of definitions, okay? So you really need to be making sure you're going back through these things, looking them over so that when it gets to test day, you're going to be just fine. All right, class. Look forward to seeing you next time. All right. Happy mathing.